Okay, so just a little bit about where the implementation for Zarr is in the SDF libraries and what Zarr is and the data models, how they compare, and then a bit about about other things in the cloud with netCDF and yeah. Anyway, oops.
Yes.
Yeah, I was. Okay, so Zarr has been around for a while, so I'm not going to cover that a lot. But if there's any questions, we can talk about that some more. But the Zarr model, data model, is very similar to the netCDF model. netCDF4 has some netCDF4. Well, yeah, the netCDF4 model. So then NC, but there's some things missing like shared names, dimensions, and unlimited dimensions and other things. Scalars and strings. So NC-Zarr is a metadata kind of convention, a few extra attributes that get stored in a Zarr file to represent some of the bits of netCDF4, the netCDF4 data model that aren't in the Zarr, so that we can have enough information to map between the two without any loss of information. An NC-Zarr, so they are stored as attributes, Zarr attributes. So an NC-Zarr data set is a legal Zarr data set. Just the attributes, extra attributes get ignored by other things that don't know what they mean. The netCDF libraries will attempt, if it's just a straight Zarr file without those attributes, they'll attempt to do some mapping to map that into Zarr. So which it should be able to handle all the Zarr, the full Zarr data model should fit into the netCDF with a few little assumptions and stuff about dimensions, perhaps. So, okay, so this just goes into some of the details I already mentioned. So it does support groups, dimensions, variables, attributes, all the normal stuff from netCDF3 data model, chunking, and then signed and unsigned integers. So, so a little more than the classic netCDF data model, but not the full enhanced data model. Characters. Okay, right. Unlimited dimensions, user types, and strings are missing from Zarr. So, and NC-Zarr. Charlie.
As of 2 weeks ago, they put in strings.
Oh, you're right. Yeah, the strings just got added to the C implementation anyway. Yeah. And I think that hasn't been added to, I don't believe that's been added to the Java library yet. So in terms of the C implementation, right, it's completely self-contained. There's no external libraries. It doesn't rely on any of the HDF5 code. It does use the HDF5 compression filters in some way that I'm not exactly clear on, but it uses, well, there's more here. Right, so the compressors, Zarr tends to rely on the num codecs thing and the names for the num codec compressors or filters and for codecs, and the netCDF depends on the HDF5 collection of compressors, and so they do a mapping between those two, the names of the, the HDF5 compressor that matches up with the num codec one to make sure they're using the same compressors. netCDF Java has implemented Zarr as this is kind of some details of netCDF Java that most people don't need to know about there, but there's a service provider kind of interface that can be implemented to support different types of file formats. And so Zarr was done through that interface. And it maps it into the common data model, which is kind of, it's basically the netCDF enhanced data model with some slight variations in the Java world, but, and it's, so this one supports that. And I believe the C library also supports this, but I would need to fully confirm that, but the Zarr can be stored as, so the Zarr is individual objects or files for the metadata, and then for each chunk of the data, and is stored in a hierarchical structure. So it can be stored as files in a directory structure. That can be packaged up as a zip object, and then in an object store, of course, which is on the cloud. So things have kind of where Zarr started. And yes, NC-Zarr and the netCDF Java implementation is still a work in progress. I would say the C library is too. C is probably a little further along than Java, and C has Charlie testing it. So he's found a number of issues with the C library, which has really been helpful. So we just need somebody like that to work on the Java part too. Which we have a few folks who do have different tools that use the Java library. So that will happen. It has sort of been happening, just not all the details yet that Charlie's found. This is just more details on the actual implementation in Java. And yeah, the netCDF Java uses this random access file interface that has expanded to lots of things. So let's see what else. Yeah, there's nothing new there in that slide really. Oh, and the compressors are there's another interface, service provider interface that gets implemented for the different compressors. And so we have a number of compressors there. Now, I think there might be more than this. I tried to get this updated, but I don't think we caught everything. And let's see. So yeah, it's a pretty easy interface, and we're hoping that will help us get some others in the community to help implement some wrappers around some compressor libraries. So, and we'll eventually get there too. So, so this is again Zarr and a few other things. Just want to mention a few things, other things in terms of netCDF and HDF in the cloud. So most of this is Zarr. Sorry, I'm not sure where I'm pointing here at the screen, but most of this is just about Zarr in the C library. But the C library can also read, well, the Java library can also read netCDF or HDF files in the cloud, just using byte range requests and figuring things out where they are, and it's always been able to do that with the netCDF 3 as well. And I believe netCDF C can also do that. So an HTTP, if just a netCDF file is behind an HTTP server, it can use byte range requests and grab pieces and understand what's there. So there are some other efforts in that realm as well. This last little bullet on this slide, the OpenDAP group has this DMR++. It's basically pulls out an index to a file sitting somewhere with all the byte range or the offset information to the different data chunks and stuff, and so that they can then access it on an object store. So because object stores, I think most, if not all, object stores support byte range requests. And another effort from the HDF group is the or I think it originally came out of the HDF group, or they're involved with it at least, is the Kerchunk project. I thought I had put a link on that one. But anyway, if you search for Kerchunk and HDF or something, it will definitely pop up. So there's a lot of different efforts underway in terms of, so Zarr is kind of the big cloud data format these days, but a lot of the older formats can be done as well in the cloud. It's just the software doesn't support the kind of multi-threaded access and multi-readers going after the data. So that the Zarr library does, this current Zarr library was designed to do. So, right. So future directions in terms of C and Java libraries. Oh yeah. So more compressors on both sides, and then on the netCDF Java side, implementing more support in the threads data server, right, and looking at performance issues on the Java side. And I'll just mention this because I think I presented the last 2 years, the netCDF users guide, we're still working on updating that, and it's my fault that it hasn't advanced as far as it should have, but we have another version almost done, and it just reorganizes some of that and pulls it out, because currently it's kind of linked in with the C library, and we're trying to make it more general to cover other implementations, Java and others. So, questions? That's all I have. There's just a bunch of links to things. Kevin.
I think back one slide. I was just curious about the comment about Zarr and TBS, about non-trivial performance investigation. Can you elaborate?
Yeah, so I think we can pretty much support access to Zarr data from the thread server now. It's just it's not super efficient because every byte range request is an HTTP request. It just has some drawbacks to it, and there's no multi-threading at all. It just is one reader reading the whole thing, and so looking at that, and also the thread server does a lot of aggregation across data sets, and it doesn't support that. It also looks at an entire directory structure and can serve all the data sets in there or aggregate them if it has some more information. And so it doesn't really support scanning the directories that well, though I think it has some of that in it now. But yeah, George.
This is good. Nothing you said so far is giving me confidence that this is going to scale well.
That confidence that what?
This is going to scale well. And it doesn't scale well. It doesn't seem particularly useful. Can you encourage me?
Well, yeah, that's what all of this is saying. We have more work to do. So.
Do you have like an idea? Or, yeah, we're still working on it. That's okay.
Yeah.
There are different,
Right.
I'm one of them.
Right. I hope so. No, I mean, yes, definitely. Any other questions?
When you say continued work on filters codecs, my understanding of netCDF-C is that when you've got it compiled correctly, you can access filters, third-party filters that the HDF library understands. So is that understanding incorrect, or is this acknowledging a need for filters that haven't yet been used, or what can I understand about?
Well, I guess one of the issues is the equivalence of netCDF-C and netCDF Java, and we want to try to make sure they stay in sync, and so all the data that gets written can be read by either library. The issue is, yes, with netCDF-C, you can add any wrapper. There's some work, or any compressor or filter, but there's some work around that. But so people could use things that aren't as widely available if they wanted to put the work in, and then there'd be data that other libraries might not be able to read. But that's going to happen anyway. So I'm not sure if I understood your question, though.
Well, I was just wondering, I'm not sure if I understand my question myself, to be honest. So yeah, I guess I was wondering, are you not expecting, I think you've answered it actually. So you're expecting filters to continue to work transparently if the filter is implemented at the HDF level. And the challenge is keeping that CDF-C and that CDF Java in sync in that regard.
There's the effort to keep them in sync, but I think there is some effort involved. It's not just that netCDF-C can use anything that the HDF library supports for Zarr. It can use anything that HDF supports and the library is linked to locally. For writing netCDF 4 files, HDF files, it can use any of those compressors, filters. But for the Zarr, there's an extra step because it's not actually relying on the HDF5 library. So there's some wrappers for the particular libraries, I believe, on the Zarr side, if that makes sense.
Right.
So it takes more work to use a new filter to write Zarr than it does to write HDF5 based netCDF4 files.
But you could do something like use netCDF-C to read a netCDF4 file that's using a filter. So it delegates the filtering to the HDF library. You unpack that in memory and write it to a Zarr file, however you like. You're not forced to use that same filter doesn't need to be available to Zarr. It could take the unpacked data and write that in Zarr format.
Right.
Okay.
Okay. Any online questions?
Yeah, I have one.
Okay.
So the implementation of Zarr in HDF SCSAC is based on the Amazon library.
Based on the
Amazon package or
the
SDK.
yes, I believe both the netCDF-C uses the Amazon S3 SDK, the C++, I believe, library, and the Java uses also the Java SDK for Amazon.
Outside the S3.
Yes, it does. Like here, and I don't have the list of everything that's been tested on for netCDF-C, but for Java, it's tested in AWS, so the S3, AWS, Google Cloud Storage, Microsoft Azure, and a few others. And I can't remember the other ones, but so yeah, it does support other.
Another question.
Yeah.
We know if it is possible to embed stored inside an NCML file right now.
Inside an XML file. I think you can reference a Zarr file from inside NCML and have the netCDF Java library read it. Yeah. Charlie.
Just wanted to add something to what Daniel's point about the filters. My understanding is that you're exactly right about the additional complexity of referencing some of the codecs that Zarr is used to using. But most of that work has been done in the sense that most of the Python applications that like Zarr use the BLOS compressor library. And that is a sort of a one-off piece of work that is already in netCDF-C. So all of the BLOS codecs can be referenced. And there's a BLOS 2 that's on its way into development, and that would require another sort of set of work. But the template that has been laid out, that's going to stop any information we do that. And then, yeah, so the C library is pretty darn mature right now for Zarr. The issue is in whether or not the Java applications are going to be able to read things that the C library has written at the Zarr level. But you're right, there is that workaround that you could use. You can always dump it to an HDF file back end, and then the Java could read that. And then with regards to this last one, I wanted to also chime in that the Amazon library link, the C++ SDK that you mentioned, is a weak point in the whole framework because nothing to do with Unidata, but that is a very large piece of software that does not install in many package management systems like it does work on Ubuntu. You can get the package installed, you don't do any work, install it. But I think with CondaForge and with Homebrew, you're not going to get netCDF to build and link to that library without some trouble.
Yeah.
And so, since the real market for this is kind of using it on S3 storage, that's a big issue.
Yeah.
And I don't know how it's going to eventually work out.
Yeah. There is a C SDK as well, and I think there's two of them, Amazon based ones, and I don't. And Dennis has had trouble with the C one as well. He's tried both, building them and stuff. So I don't. Yeah, it's not as well supported as the Java one is actually pretty solid and doesn't have all the build issues. But so yeah, that's definitely an issue.
Okay, so Bryan wants to say something. Bryan?
Well, Klaus was first, I think.
Okay, sorry. Klaus?
Thanks. Yeah, I just wanted to ask about the Python API. That's based on the C library, as I understand it. So I'm eager, and I'm sure others are too, to play around with Zarr through that as well. Are there any plans on that? And maybe as a side comment on that, it might be helpful to add to the documentation of that which version of the C library it is based on, the current version.
Right, and I think there was an issue on that repo that, so Jeff Whitaker, thank you, leads the Python wrapper effort, and I think he's been working with somebody. There was an issue raised about the Zarr work, and I think that's going to be an issue. The one that Charlie just brought up is going to be an issue there, and I think what the issue was that did come up was the different codecs and how they're linked in the libraries that it gets linked to, and they weren't getting built into the Python distributions, the current Python distributions. And so Jeff was working on that with a few folks, and so hopefully that will move forward pretty quickly. I think I don't really follow the Python wrapper that closely. If there's missing information about what version is built, then I guess probably it would be good to raise an issue in that repo and ask for some additional information on the website or whatever. But so, and then it depends on the build or how you install it too, I suppose, if it's Conda or if it's pip or whatever else it would be. So I guess that's all I know about that one, really. All right. Did Bryan have a?
Bryan, please.
Yeah, a very, very different question. As I understand it, all of the decompression happens in the software stack that's sitting underneath netCDF, so that when you want to slice into a chunk, you have to load the chunk and decompress it in your software. Is there any prospect of passing to the server when you do the byte range request, actually the byte range of the chunk and the slice that you want in it and the compression method, so that the server can do that? I'll fully motivate that later on this morning, but the question is quite tight here, I think.
Well, I mean, certainly it could be possible, but one of the things, if you ask anybody in the Zarr community about a server side anything, they'll say you don't need a server, you can get to the data yourself, just get to the data and do whatever. So that they tend to focus on that. I definitely agree that server, there are some things that maybe would be great to do on the server and send back, but that's But we haven't really looked into that. The thread server maybe will do some stuff in that realm. I guess I'm not sure what that would look like in terms of Zarr. Though I will say the Zarr library folks, the actual folks implementing the Python Zarr library, are looking at ways of exposing the chunk sizes and locations and all that information through the API. So maybe there is a way to, I'm not sure.
There's already information. Yeah, no, fair enough. I think that's fair. I think I'll motivate later on why I think you can get to the data requires you to have a server-side something. But
I'm with you, but I'm not sure everybody else is.
Yeah, but I think Kachunk at least allows you an index, and that's probably what they would expose in the case of netCDF. Anyway, David can probably talk to you some more about this over lunch if people want to follow up why I'm asking this. We're not really ready to talk about it in public yet, but we're happy to talk about it over lunch.
Over beers, right?
Yeah.
All right. Thanks.
Just Bryan, this is Antonio speaking. Just one comment about this, because you are talking about the block on device, on drivers, and we are talking about file system. In fact, what we are saying is we are moving to the server of the compression, like the CSIC-UC, for example, that is making all the compression with different algorithms, and it's being done the file system itself.
Quite. That is the thing, right? If you believe in systems doing compression and decompression, you've got to start handing the system information about what compression and decompression you're playing with.
Yeah. I mean, we are starting to talk about that because this is a software or client side compression and decompression, and the server side is the file, almost the file system or the storage system itself in the server side.
Yeah. So I've got some diagrams and discussion of this to come later on this morning.
Good.
Great. Yeah.
Great.
All right. Any more online or here questions? All right. Thanks, everyone.
Okay, I'm going to introduce myself. This is Antonio Cofiño. This talk was very, I mean, this was the intention of trying to explain what is geometries and grids on the CF, but I think I didn't comply with the whole objective of this talk, but at least I will give just a briefing, and it's in fact one point of view that I have about this part of the geometries and grids on CF. This part is relates about the topological concepts that there is already in the CF itself. I'm not talking about coordinates itself, neither. Okay, they are going to appear and so on. But all this stuff is related with the discrete sampling geometries, and also with the intention to incorporate the U-grid into the CF document. This concept plus the geometry section refers, and the document refers about the mathematical and the topological order of the points on the CF conventions itself. That relates, of course, with the cell method, but it's not only about the cell method, because the cell method refers to a domain, right? But the domain with these topological concepts refers not only about the cell, can be referred to the vertex or the nodes of the cell, or can refer to the surface or some edge and so on. And if we are talking about the multidimensional concepts, the mathematics becomes very complex. Okay? I'm not going to talk about that. I'm just trying to give a point of view that this part of the CF document, that was the reason because of my question the first day, because it's starting to grow up and we are starting to mix things. I'm not giving any solution. I'm just giving a point of view of what is there. I mean, it's not any solution. And it's because I am discovering that this is some kind of relationship or topological relationship between data inside of the CF convention itself. I mean, it's not about the physical quantities itself, and it's not about the coordinates itself. Okay, it relates, of course, because we are talking about geometries or geographic coordinates and so on, but it's not. I mean, it's not the same concept. They are separate concepts because the part when we are talking about coordinates refers, geographical coordinates refers to coordinate reference or coordinate reference systems as also the time concept, for example, or when we have the mathematical concept two-dimensional times, for example. That is a quite nice example of a kind of physical concept, but we have two-dimensional, like the reference time or the forecast time, for example, in the same days. And this, for many community users, it's a quite complex concept, but it's very easy to encode in the CF. I mean, it's no problem encoding that kind of information in the CF. And I say, I pretended to give a talk on that, but I didn't make it, I think I made it in a good way, and then I will just a small introduction to this. I don't want to say issue, okay, but this discussion or this something to think about the CF of how we're going. I mean, because we were talking about long time ago about the CF 2.0, for example, and I think it's something that is more on that. And also we are talking also about the CF core, or what is core or what is not core, or we are going to define namespace inside of the CF and so on. I think it's more for the future than for the current. If I have to start for something in the CF document about explaining these topological ideas, I'm talking about the chapter on discrete sampling geometry, chapter 9. I think it's the best starting point for talking about this. It's one of the chapters that appears in the CF version 1.7, 6, sorry. It's a quite large part, and it's a quite complex part of the CS document. Was coming from Unidata conventions, so about encoding also observations and time series and trajectories and so on. And the quite complicated thing was the topological thing about encoding time series, because all the time, and many of the examples, of course, was related to multidimensional structure. And then we need to encode some that is not multidimensional into a multidimensional array. Okay? And that was a challenge in many years. The discrete sampling are multidimensional features. Okay, they are multidimensional in fact, but they are stored in the netCDF in this concept of array with multidimensions. The point of the discrete sampling geometries is that they have a lower dimensionality. In fact, in this hyperdimensional, multidimensional, they have less ranks if you want to talk about, or dimensions not dimensions, dimensionality, right? Less dimensionality with respect to the space-time domain. Many of the examples about the discrete sampling geometry refers to for example, to time series or vertical profiles, trajectories, and so on, and points also. The discrete sampling geometries are usually feature collections. That means they try to sample some feature, okay, and it's a collection of features. And this collection of samples of a discrete sampling geometry is like a single trajectory, for example. As I say, the discrete sampling geometries data sets are usually feature collections of samples of like a single trajectory, okay, and they are identified at instance of itself, okay, and this provides a unique ID for a discrete sampling geometry, and also we have a variable stored in the data itself, like observations, for example, okay, and this is something that is quite difficult to understand not difficult. You need to read and read again just to understand well in the chapter of the discrete sampling geometries. The instance dimension, the I, for example, that is being encoded and is not as I in the document, is used for identify a particular feature in a collection of features. The language starts to complicate, okay? Variables with only instance dimensions are instance variables that allows to us to identify the instance itself in this space, okay? Which provides descriptive metadata. This is about descriptive metadata of the instance itself, okay? For individual feature of the instance. The term element, the O, the notation in the document, is used to distinguish data elements composing a single feature. I will show you some examples later, just try to introduce, because for me, this is something quite complex, okay? Also, for example, in a collection of time series features, each time series instance, the I has data values on each time, O. All right? In the discrete sampling geometry, there is 6 features, okay? Sorry, features types we need to encode. This start to grow in complexity inside of, okay? And there is points, this is the simplest one, okay? There is time series, there is trajectories, there is profile, there is time series profiles, and there is trajectories profile, okay? They grow in complexity, okay? They are growing in complexity because to understand them. And one of the things about the CF, and something that we need to override in some way, in some moment, but I don't know when, okay, is about the CF just allows 1 feature per file, because you need to annotate in the global attribute about that. And this is a quite issue, okay? Or maybe we can do it in the groups, I don't know. I mean, for me, it's quite confusing on that. All this being explained very well, very well. It's explained with a nice example, because something that is very useful in the CF documentation are the examples, because you read the text, it's okay, you can read and just, because the terminology is also complex, but the best tool in the CF document, the convention documents, are the examples. And in this case, the most useful part of the CF document for the chapter 9 are the appendix H, to understand everything. And also because in the document, the chapter 9 is mixed with the storage, how it's being stored, the data itself, how it's being arranged, the data on the file itself, on the multidimensional thing. And then both things are mixed in the document, and it's quite complex to understand in some ways. And then you need to go to the appendix and try to see the examples and going back and forward, because one thing is the topological connectivity of the things, of the instance, the observation, and so on. Another thing, how the data is being laid out on the array. I'm not talking about the storage itself, because it's another problem, as Ethan was speaking before, about the Zarr, because the Zarr, the compression and so on are related with the storage layer itself. And this is more related in the middle layer about storing in an array, how to store information in an array, okay? But the discrete sample geometry is a higher concept, okay? Because it's talking about the mathematical topology of the data, the connection between the data. And from my point of view, there is 3 kind of layers on this thing. As I say, there is the mathematical topology connection, the middle layer about the disposition of the data on the multidimensional array, and then the storage layer just below. That is netCDF, or the middle layer is the netCDF data model, okay? And the storage layer is in the case of netCDF Quad 4 with SDF, it says HDF5, okay? This is different levels of storage and models. Okay, I'm not going to go into too much detail, okay? Because just I'm trying to show making a very small introduction about this. The coordinate or auxiliary coordinate variable that contains the attribute CF role is which allows to us to identify the object itself, the ID of the object. I need to look into the variables, which one has the attribute CF role, and I will use that variable to identify the different objects in the features type, okay? This variable must provide a unique identifier for each feature instance, okay? And the dimension of this variable identifies the instance dimension, which allows to put IDs to the instance. Some examples, okay, with the profile. For example, profile is an ordered set of data points along a vertical line and fixed times, okay? Sorry, fixed horizontal position, and fixed time. This is fixed. There is no movement on time, or there is no moving on space, okay? This is a profile. The typical examples are, a profile is a series of connected observations and of vertical lines, like atmospheric or ocean soundings, okay? Approach, I mean, they are being approached as a vertical. In fact, they are not vertical, but this is another problem, but they are assumed that they are in the same vertical at the same time, okay? And this one of the examples, okay? The profile contains 2 logical parts, one part is the observation itself, with the instance and the elements dimensions, the data instance, and here is the O is going to be the height, or sorry, the height or the depth, depending if it's the atmospheric or the atmospheric sounding or the oceanic sounding. Okay. And there is some mandatory coordinate variables. One coordinate variable is the X position. Yes, it's fixed. It just depends only on the instance itself. Only on where is the ship, for example, the point in the space. And there is also the T, the time, for example, in this case, also that is fixed, and the zeta. The zeta is the height. That is depends on the O dimension. On the right, you have one of the examples. Okay, that we have the ID is being given by the profile variable that says us this is identifying the kind of user tag, the CF role profile ID. Okay, and is telling to us that this file is providing a profile ID. Okay, the type of this data set is the profile ID, and there is 3 observations like the pressure, temperature, and humidity in the 2 dimensions, profiles and zeta. Okay, the I dimension and the O dimension itself. And then we have the O dimension or the coordinate zeta, that is the depth. This is the altitude. The position on the horizontal space, that is the longitude and latitude. And about the profile. And this is the dimension is the I instance. Okay, that is related with the profile itself. With the profile that is identified the variable. This one is a small example. The important concepts are the I concept, the O concept, the instance concept, the element concept of O, and dimensions, and so on. And here the coordinates are the longitude, latitude, zeta, and time, and the data is pressure, temperature, and humidity. And the profile variables giving to us the ID of the different instances. Discrete sampling dataset can contain can contain one or multiple profile measures. The number of profiles is specified by the instance dimension, in this case 142, and at least one of instance variables with CF role attribute has to be set to profile ID. The attribute profile ID. In this case, the profile variable. What about time series, for example? This is another example. Okay, this is less complex than the profile, but it's just showing the same concept. Time series is a series of data points. It's very easy, more or less easy to understand. And the same spatial location with increasing times, okay? The increasing coordinates or times. Time series that is taking over periods of time a set of discrete points or spatial locations, okay? The typical examples are observations in different points or in different stations. This is a typical situation, or the weather stations, for example. They are fixed in the space, but they are taking samples on time, usually in a regular time. Okay. The logical structure. This is the logical structure of this data set. Is of time series data contains 2 parts: observation variable with both instance and element dimensions. Is the data with dimensions I and O, and the mandatory coordinate variables. That in this case, this is the space 1, the X and Y. And the zeta that depends on the I and the O, okay? The observation itself and the time. So, in this case, we need at least one instance variable of any data type, of course, with the CF role time series ID to identify this data as a future type of time series. Oops, I lost this. Sorry. The typical example for time series is the weather stations time series. Okay, we have the humidity in the observation variable. We have the humidity. I don't know which. So, yes, the first one. The coordinates is the long, the latitude, the altitude, also the latitude. The variable station name in this case is the instance variable with the CF role attribute set to time series ID. In this case, is just below the one just below, and this giving to us the identification, the ID for each of the instance of this. In this case, for each of the weather stations. Another example is the trajectories. The trajectories is another example of this discrete sampling geometries. In this case, the trajectory is a series of data points along a path, okay, through a space with monodic increasing times. Okay. Trajectories data is taking along this discrete path through a space. Its path constituting a connect set of points. They are connected. Again, the trajectory, the important topological concept is that they are connected. Again, in the time and the space. This is an important concept. Example of that are the zip path or the tropical cyclone tracks, for example. These are typical for trajectories. The logical structure for this example, I think, contains two parts: the observation variable, the data itself, and the coordinates, the x, y, zeta, and t. Just in this case, all the coordinates variables has a dimension, the instance and the element and the O dimensions. And this is what defines to us the kind of time, the trajectories. And at least we need to have one instance variable with a CF role set to trajectory. Okay. There is just one example of considering the concentration of NO3 or 3 or CP, or some, sorry. They are the observation variables in the CDL. I don't know what they are just below. Down the CDL. The coordinates, in this case, the coordinates has dimensions, trajectory, and observations, and the variable trajectory is the instance variable with CF role attribute trajectory. Just the one in the trajectory variable with dimension trajectory, of course. Okay, these are different examples, but the most important thing about the discrete sampling geometry is the topological connectivity and the definitions, and this I think is the most important part. What is explaining also in the chapter 9 is about how to dispose the data, but I didn't talk about how to dispose this data on the array. Okay, so sorry, yes, on the array, because you can dispose in in some ways. But I think the most important part in the discrete sampling geometry is just the explanation of how to encode this different connectivity of trajectories, time series points, profiles, and so on. And this can be extended, or is being extended, in fact, in the CF document, okay? Because in the CF there is geometries, and there is this kind of concept geometry is when we are defining the cells. In the cells, we are defining the boundaries. Because we are defining this concept that is the boundaries that defines a cell. We need to define that. And the thing is that for many geospatial applications, I say that they are associated with a geometry, with a spatial representation of a real world feature. Okay? This is the same concept again as the discrete sampling geometry. But this is a different chapter. Okay, sorry, this is in a different section. This is being explained in the CF document in the section 7.5, I think. I don't remember. I will section 7. No, 7.5. This is explaining in section 7.5. Sorry, but when we are talking about the CF cell boundaries, because this is the mathematical connectivity of the data, is being explained when we are talking about cell boundaries in the section 7.1. This is a different part of the document. This concept, okay? Because the boundaries is defining a kind of the connectivity of the geometry where it's leaving the data, right? This is the cell, okay? The cell boundaries allows polygonal cells, but every cell must have the same number of vertices. As you can see, this can have many limitations. Okay, and then there's many limitations, but this is one of the examples in the document in section 7.9 about how to define a boundary. Sorry, the boundaries for the latitude and longitude with multiple brackets, in fact, but all the boundaries of all the cells have the same polygonal dimensions or size, in fact. But if we are talking about cells, we need to understand also that there's something that is called the structure grids. And this part is being explained when we are explaining in the document the coordinate systems. And then we are talking about the 2D longitude, the 1D, the independent coordinate longitude and latitude, but there is one explanation about the 2D longitude and latitude coordinates. And also it's being explained there, some relationship. And then in the document, and then the trick that we find, I must say that we find many of the data sets. This is the two-dimensional longitude and latitude, because we need to define the boundaries of the curvilinear grid. But usually we find many of the times the independent longitude, the independent X and Y. Okay? Yes, because we sometimes, for making the representation easily, we need this information just to draw the data and to have a better. But the real topological information is being provided by the long and the lat, together with, not the long and the lat, the boundaries of the long and the lat. That is giving to us the topological information. And this is in some way explained when the document is talking about in sections 5.1 and 5.2 about the two-dimensional, the independent dimensions, coordinates, and the two-dimensional coordinates, no independent. As I say, this is just one example, and this is just one point of view of my view of when I'm reading the document, how I see the document, and trying to encode many of the information. Because when I try to understand this, I think that I see the potential at just to encoding many other mathematical topological concepts that are not necessarily related to time series or profiles or grids. Okay, as I said before, I mean, for example, the time. The forecast time and the valid time, they are quite two nice concepts inside of the document, and they can be encoded, but they are kind of connected in another way around, also in a topological way, in mathematical topological way. I'm not talking about coordinate itself or the reference system of the time or the reference system. I'm talking about the connectivity of the data inside of the netCDF files. I mean, I don't want to spend many of these because there is the CF geometries. There's one new section on the document about the geometries that tries to define the connectivity about lines, polygons, surface, and volumes. I'm sorry, I forgot if there's. Yeah, there's volumes, I think. That we want to define physical quantities, maybe in the vertex, or maybe in the edge, or maybe in the face, or maybe in the volume. This is quite important topological concepts to define. And this is the reason I didn't put here, okay, sorry. Well, sorry, the geometry section 7.5 is defining the geometry containers and so on, many other new concepts. And this becomes a very, the problem is that you have to remember many things. It's not easy as seeing a Cartesian or square or array with grids. Is quite easy to understand. This requires a more interpretation of the CF, of the CDL. Just try to understand what is being encoded on there. And try, but following the instructions is not too complicated to understand, but you have to remember many things. And one of the most not confusing, but that is mixed with when you try to understand what is the topological connectivity of the data, is when you also has to understand what are the coordinate reference of the data also. And this is quite complex for many people, okay? This is quite complex. Okay? When you need to define the grid mapping, for example, because also you need to georeference. I'm not talking about geometry, I'm talking right now to make a georeference and geodata. This is the role of the coordinate reference system. Okay, yes, this is just a review of this, okay? I'm not pretending just to give any solution. And as David said in the first day, the thing is going to become very, for me, my point of view is that when the U-grid is coming, the U-grid is a nice convention because they find many quite interesting for unstructured grids because it defines physical quantities related with the structural grids. As I say, they define concepts for volumes, they define concepts for fluxes through a surface, for example, or or variables over a path or edge and so on. And it's a quite convention, a nice convention, but when this convention is going to, I mean, my prediction for this is when it's coming to the document is going to grow big and start to be to complicate a lot of, as Alison was explaining one of the, on her talk about using the standard names as a sync for everything. I think it's when the grid is coming is nobody. I mean, when I say nobody, few people are going to use all the capabilities of this kind of encoding. And because I think we need a more structured document, just trying to separate many of the important concepts that appear in the document. This is just my point of view and my impression. Okay, it's not. Okay, thank you. You can make questions, but I don't know if I have answer or comments. Comments, I prefer the comments.
There is a question in the Google Doc.
Sorry. Good question.
You want me to read it?
Yes, please.
So it's a question from Andrew, and he asks, how will these geometric and grid concepts apply for extraterrestrial activities?
That's a good thing. I mean, because if you stay with the job, I mean, for extraterrestrial, I understand other planets, for example, or
it's related to the aviation industry planning for flights that are supported.
sorry, yeah. Well, yes, this is on the field of the this being applied because also there is concept for radar, also for Schwartz, and so on. I mean, they can be applied because the most of the challenge for this kind of data, in my opinion, is the encoding the topological and the connectivity of the data, because the grid or the logical, I mean, is moving in the time and also is sampling in different spaces, and it's a kind of swap in fact, and something that is missing. No, it's not. It's missing in the, for example, in the future studies, the swap concept, for example. But I think it's already there because somebody, Alexander Jenner, was encoding this kind of information on the CF, and he was spending a lot of time in encoding, putting example of encoding SWATs, because it's quite complex also to encode. That's another example, because another example of the complexity is, I mean, the specification is good, but for any new to this concept requires expertise on SWAT to understand that one. I mean, of course, it's for someone that wants to encode this kind of information, but I'm not expert on that kind of data. And to me, for example, to understand this thing in the CF document is quite difficult in many times.
If I remember correctly, the issue with SWATs was the main issue he was encountering was the one feature type per file.
Yeah, that was the one. I didn't say, but one of the things that I see the real limitation on the discrete sample geometry is that global attribute saying the kind of, because for me, and this is for me, it breaks the idea of the good idea of the CF documentation that by default all the global attributes are applied to every variable. You don't need to have only the conventions global attribute. In fact, you don't need anything else. And all the global attributes, in fact, is a way of just packing all the info of metadata, many attributes in each of the variables, right? But when the global attribute, I can't encode in the same netCDF entity different concepts for the future. Sorry, different future stuff.
Yeah,
it's a limitation. I mean, because I understand why it's there, but it's quite limiting thing.
That can change.
Good.
The history, as I understand it, is this was debated at the time that it went in. That the argument was, well, there's only one piece of software that encodes this.
Yes.
And it assumes one feature type file, so that's what's going in. That one said, but that's not true anymore. So there's definitely more than one piece of software that fully encodes all of the speech sample.
Maybe I'm wrong, but I think
it's an enhancement we put in.
Yeah. Maybe I'm wrong, but I think it's the only global attribute. It's the only require global attribute except for the conventions. I'm not sure, okay? I'm not a. Yeah, could be. Could be, I mean.
Yeah.
Because-
What's the feature type?
Sorry?
Which attribute?
Feature type, yeah.
Future type. The only required attribute, global attribute, is the conventions. Attribute, global one.
Yeah,
The other ones, you can put into the principal variable, for example. Or different variables, I mean, the source, the comments,
a feature type has to be a global attribute
yes.
currently.
It's
Yeah,
not-
it's-
And then, no, the problem is not using.
It should be able to be a group attribute.
Yeah, that's the reason because I put that question, because when we started working with groups, I say, okay, we can move that to.
So, but even more flexible would be to have it attached to the variable, the data variable,
Yes.
right?
Or a container variable that where is the.
You could attach it to the data variable or use scoping to implicitly attach it. So, I mean, there are multiple ways of doing it. Yeah.
Right, but so many things are already written in this, the classic data model, it would be nice to be able to handle it in a classic data model
Mm.
way.
Yeah.
That's why a group attribute.
Well, that's not in the classic data model.
No, but it behaves as if it's a classic data model within a group.
When you translate back
Yeah.
to classic, you take those.
You flatten it.
attributes, You flatten them out. into-
Yeah.
So it's equivalent.
Yeah.
Good.
Yeah, no, I've actually thought, I mean, in years past, I've thought maybe this is something that we should try to tackle as an enhancement, like David was saying. But I wasn't aware of anybody who is saying, I want to use this right now. And my preference is always to change the conventional ways that we know will be used. Otherwise, you make something that's beautiful and it handles every use case, but it's hard to
Yeah,
understand.
I agree with many of, I agree with this philosophy on CA because we need a practical use of, because we are not playing. I understand, and when I was talking that we need to re-encode or to refactor the document just to put in the better way of the mathematical topology connectivities, the coordinates and physical quantities and so on. I say, no, but I know that the document has to be for practical purposes. When I read the document, I try to conceptual, make an abstraction of what is there and try to understand. I understand that there is practical, as you say. We need to find. I understand that many people that is encoding time series is not going to encode other kind of future types, the community, and then for them it's not limitation because I see that they are not exploiting all the capabilities of putting inside of an netCDF many variables, like using one of the things that also I see in many of the examples, that is, I'm not saying that it's bad, but I see how the people are understanding the CF standard, that when they are defining the longitude or the latitude, the dimensions, they are calling the dimensions longitude and latitude. And then that provides a lot of confusion because they think that is the coordinate is not. The dimensions can be D1, D2, D3. I don't care about what is the name of the dimension itself, and I don't care about what is the name of the variables itself in the netCDF entity. I need to go to the attributes and to understand what means that. But in practical situations, when the people is encoding, it's just taking the course philosophy and that is being percolated into the CF, and because there's many data, and I understand it's easy for the user to encode that way. But you don't need to that because you can have one longitude, long 1, long 2, long 3, and so on. You can do that, but for people it's quite confusing. Because they are all the time are seeing files with longitude dimension, longitude variable, and so on. And for them, there's nothing. But this is just my view.
Okay, so Klaus, want to say something?
Klaus, please.
Thanks. Yeah, I just wanted to ask or to suggest basically that it would be tremendously helpful to add a figure or two to the documentation. When I was trying to understand particularly example 7.16, which is these polygons with holes.
Yeah.
I tried to read through it, and the only way I could make sense of it in the end was to draw a picture. Then it became clear, but I think that picture should be in the documentation with labeled nodes and maybe some arrows in what direction the edges are going and this kind of information. That would clear up a lot of things, I think.
Yeah, you are right, Klaus. I think it's the same thing I said before. It's like the chapter 9 about discrete sampling geometry. You start to read it and you say, I'm going to examples and just to understand. That's a very useful part of the appendix 8, because when you go there, you understand, and then going back to the chapter 9, and then, okay, I start to understand.
Yeah, I understand. It's no criticism. It's a tremendous amount of work, and I'm very happy to see the bits in that are in. But I think that would be a great next step.
Yeah.
Your pull request is extremely welcome, Klaus.
Well, I suppose one question with regards to that I always face is, should we have a kind of standardized approach to doing this kind of figures? We have a bunch of figures in there, and I always wonder, is this something that we should do with SVG or some kind of drawing library? Of course, I would put forward also LaTeX and TIX, but yeah, I don't know. Would it be good to have the notion of having a standardized approach in the conventions to figures? Obviously, this is going way beyond this talk, so I don't know, but something to think about maybe.
We might consider discussing this in the afternoon hackathon session if you got time there.
You understand, Klaus?
Yeah, sounds good.
Yeah. Okay.
I just say on that figures, it's not always possible, but if they can be the source code that produced it be included, that's really useful.
Yes,
That's not always possible.
So maybe we convert the CF conventions document into a notebook.
I would go beyond Jupyter book.
Yeah, that's what.
No, when I think that one of the places that I see these kind of things is in the new training thing. Okay, because you not in the document itself, because could be, but because then we are starting to again grow the document, but moving to the training, some special paths as we have the what's called the request. No, sorry, this document that is the requirements document, right?
The conformance.
Sorry, the conformance document. We have and nobody's looking at. I mean, nobody. It's important document because if you want to check many things, it's a nice document to take it, and yes, I need to check this, and this. I think it's nice to have a kind of example document or training document.
We need loads of examples.
Yeah.
Somewhere, whether it's in the training tool.
Yeah.
Loads of examples, loads of diagrams.
We need to collect many examples, and that's to understand many examples. We need to collect them and then to classify them and then try to put in the. But I don't see that it needs to go into the document, the conventions document, because
it could live somewhere else. But
Yeah.
we do need them to make it more usable.
Yeah.
We need a library, like example files, example metadata,
Yeah.
you know, how I made this file,
Yeah.
all of that stuff. Would be very
Yeah, I see like that. Yes. Okay, I don't think there is more comment.
Right. So you'll see the titles change, and really what you might consider my talk as being a glorified introduction to Charlie's talk. This is a bit of a ramble around some reasons why we care about compression metadata and compression in general. But there are a few differences from what I think Charlie's going to say. And but I think we've organised the session so that I'll talk, then Charlie talks, and then we can maybe have a discussion rather than sort of preempt what Charlie says in the discussion after mine. Okay, so what I want to do is give a bit of context, discuss a little bit of information content, really as motivation to different aspects of some of the things we've already talked about. A little bit about one slide on how compression is done, because that's not really what today is about. A little bit about where we do compression, because I think we have to start thinking more about that, in particular decompression. quite a bit more on trust and on requirements, which heads towards what we might need to consider for CF. Much of the content in this presentation was lifted from presentations at an online workshop held earlier this year, and hopefully I've managed to acknowledge all those speakers directly, and should this ever get written up, we'll write it up as a joint thing. Anyway, so charging on. So you've all seen graphs like this, and you can't read any of the axes because they're too small. But basically what they are graphs of compute usage at 3 different places, which are the red things, and they're nice exponential straight lines over decades, and storage at all those places, also exponential straight lines over decades. And the bottom line is that storage is getting really expensive and very slow, and this can't continue, and we all know that, which is why we compressed CMIP6, and we will do more compression in the future, but we use lossless compression, and really to make a big dent in this, we need to start using lossy compression, and that has a lot of implications. So reasons why we don't use lossy compression, or in fact often don't even use lossless compression, is and why we also write out too much data, is actually what we generally do is we write out every field we can think of because someone might be interested, and we write our fields out at some resolution which actually exceeds the information at the resolution, never mind the information in the bits, and indeed we write out the numbers with precision that exceeds the amount of information in the actual numbers themselves. And we don't use easy compression options because we, or somebody else who has some influence over us, believes that lossy techniques might introduce analysis errors, potentially for analysis that will never get done. We think it's too slow. We don't think we have software, and we're worried that we, or indeed users in a few years, might forget what we did in the way of compression and be either unable to decompress or misuse the data because they didn't know about the decompression. And these, of course, the last few of these things are things we can do about in metadata, do something about in metadata. So I just want to go through a little bit, some reasons. I mean, this audience is probably less interested. Some reasons why we might not write data out at all at the resolution we started thinking of, but because I think it's important. So many of us deal with numerical model data, and we have this desire to write out every grid point in our numerical model, even though we know that many of the grid points are actually only there to support the numerical differentiation, and this curve that you can't quite see shows a big dip down. The information content should go like that, goes like that. What that's saying is, in this resolution, the information content is being removed effectively by the numerics, and so there's not a lot of meaningful information there at all, and so there's a certain number of multiple of the grid points that you probably should really just do some subsampling or meaning before writing it out. And if you did that, just for free, effectively, because there isn't any information this down here, or not much, you would get obvious and easy savings. There are some places where that's not quite true. You might have land surface things where you've got gradients, but in general, most of our grid resolution is wasted in storage, and that's something we need to think harder about. But of course, if we do start reducing things, we might need to tell people we've done it and how. Obviously, the things that are interesting that are going on are located in time and space, and actually often you'd be better in the right-hand case here using features, CF features, rather than CS discrete geometries rather than grids, or in the left-hand case, look at using some kind of unstructured grid rather than a structured grid writing out the data. That's whether or not you had a structured grid in the data in the first place. And then the numbers themselves, and we often carry far more precision in the numbers that we've gotten better, I think, at turning 64 bits into 32 bits. But a lot of people are worried about any further compression because they're worried about the users not being able to do the right thing. But what people don't know is, most people don't know, is the Met Office has been binary compressing its data by quantization literally for decades, and using this WGDOS compression, and they pack some variables down to quite a few small number of bits, and some they don't pack at all. But CMIP3 and CMIP4, CMIP3 and CMIP5 users didn't even know that happened. There's less compression for climate than they use for numerical weather prediction, because for NWP they really don't need much precision in the output data. And in fact, there's a recent really nice paper showing there's actually very little information in most variables. So there's obviously quantization has been happening, done by some people, but you wouldn't know because you just get some compressed data. You don't know that the information has been removed. There are, of course, a plethora of methods for doing compression and decompression, but they're all some combination of a lossy data reduction, a lossless compression, and something clever in the format. And you might do no lossy, some combination. It could be zero lossy, and just lossless, as we did for CMIP6. And decompression obviously involves unpacking the bits and bytes, and then decompressing them. That's 2 steps. And clearly decompression depends on knowing what compression has been done. Lossless decompression can be effectively invisible to the is effectively invisible to the scientist. You even have to do netCDF minus S, NC dump minus S if you want to know that your variables have been compressed. But you can find that out. But it's effectively invisible. But lossy compression is far from invisible to the science. And actually, although we don't tend to think about it, how the compression was done across chunks and fields might actually be relevant to software. We don't really think about it because of the way we currently do things, but I'll come back to that. And right, so we're kind of used to, as I was saying earlier this morning, doing our compression and decompression in the software stack of the client, the writing client or the reading client. And we had a little bit of a discussion this morning about a lot of people don't think that's a problem. After all, their compute and their storage is all in the cloud, and you don't need to worry about it in that situation because the cloud vendors are worrying about making things efficient for you. However, I think that's a bit of a dangerous thought, because there are many cloud vendors, and many of us won't be putting our data in the cloud. But we'll be making our data available to other people via cloud APIs. So there is already a separation of concerns between where data is stored and where it's used, although that's kind of irrelevant if everything's in the one cloud or it's all sitting in your HPC in your basement. But it starts to be very relevant if you're going to have data spread out across multiple public clouds. And so you're going to have to start worrying about the data movement yourself and worrying about multiple copies of the data and all the rest of it. For the record, the 3 pictures there are, I think, NCAR, DKRZ, and CORDyS supercomputers, and we've got an Amazon and a Asia public cloud, and of course there could be more institutions and more clouds. So let's just have a little bit more about where in the software stack. So the traditional view is in this diagram, which I hope is vaguely legible for you, where you've got essentially an application, has an IO library, talks to a storage API, and there's binary data in the storage. That's how we typically think about that. So we've got the data reduction going on in the application. If there's a data reduction step, then there might be some compression, decompression done in the IO library, and everything else is the file system or the S3 or whatever, and they can worry about all this stuff. And we completely ignore the client network card, the wide area network, the server network card, and any possibility of hardware compression, for example, in a tape drive, but potentially, quote, hardware compression in a disk drive. So again, in this view of everything scattered across the world, you could well be moving a lot more data than you need to, because as soon as you do compression and decompression, you have to decompress on the chunk you compressed over. And then you can do a slice into it, because the whole point of chunking is to make slicing efficient. So nearly all use cases of chunking ought really be using slices into the chunks. So by definition, you move a lot more data to do decompression in the client. So there's a lot more choices, and if you've been following things, the network cards have got enough compute in them to do decompression on the fly. So why wouldn't the network card on the client or the server, depending on what your distribution of architecture and compute looks like, be doing it for you? Well, one obvious reason is the client network or server network card don't have a clue what compression was done, and if they did do it, netCDF would do it again. So there's some things we need to think about in terms of where we propagate information about compression and decompression, and I think they're metadata problems, though perhaps not CF metadata problems. Okay, so coming back to compression in terms of trust. So clearly, if we're doing any of this, we can't impact negatively on people's ability to trust the data itself or to generate the results they want. And there's as I sort of led with, there's a scientific reluctance to lose any information because you never know how it might be used and analysed. And it may have possible societal implications, and you don't want to change conclusions, which means you have to evaluate the information loss, and you need appropriate metrics, and you need to think about what you might be introducing in terms of artifacts or removing in terms of signal. So these are things that need to be thought about, and if they're thought about, they need to be recorded. And another, one of the things you can talk about is the real bitwise information content, and you might think you could start to encode that, but if you start, and of course you remove the insignificant bits by rounding, and then you do this lossless compression, and I guess Charlie might talk about this, but real information is not really well defined. And if you look at this little thing here, in fact, by definition, the overlap between real information and noise is an overlap. One person's signal is another person's noise. We, with WGOS compression, are happy to truncate the number of bits for wind to a tiny fraction of the number of bits that we do for climate. So it's all about application. So you need to be able to define not only what you did, but why you did it. And so all of those definitions about what you did and why are going to have to be guided by the things that you'll be thinking about, which are choices and concerns. And it could be possible that you'll realize too late. So you need to start thinking about the precision before you run the simulation that writes the data, or you'll be having to pass over the data again. And perhaps we need to understand the impact, so we need to do some measurement of the lossiness. And obviously depends on the parameter. We'll be doing a different thing with every parameter. And we might need to consider what would that relationship between signal and noise. On the other hand, there are lots of reasons why you've got to do it. I'm not going to read through those for the minute. But it's all about minimizing the data, minimizing our compute, and sometimes because our tools just stop working. Not everything can be done in the cloud. Problems with lossy compression are not only that they're removing perhaps information you want, but they can introduce interesting artifacts. I'm not sure how readable this will be on your screens, but in this case here, we have the difference between some data that was the original data and is compressed, and you can see there's some interesting wavy-like artifact in the difference. So either that wave's been removed or added. Either way, there's something interesting going on here. And then ZFP's done something different again. Here, there's a stippled artifact introduced. So knowing about those is important too. And then understanding what's going on requires some kind of evaluation, because you're worried about all these gradients, and you're worried about time, and you're worried about changes in variability because of your compression, and you're worried about changes in statistical distributions. So you need to worry about those things and measure them. And if you've measured them, guess what? You've got to record them. And you then start worrying about what the metrics are. And Alison Baker and others have done lots of work in this space, many different techniques, but they seem to be settled on this data structural similarity index, which is a number applied to a field, which is essentially, it comes from a history in vision where a structural similarity index was used to compare two figures. The difference here is you do it on the binary data before you generate a figure, so you take away all the things that are the same, like coastlines and all decisions that you might have made about how to render the figure and just consider the data. And this metric is used to choose thresholds in what compression you might use, compression ratio you might have with different techniques, and it results in a different amount of compression per variable. But it is effectively a post hoc thing. You use data SSM to choose some value. You say, oh, that's about right with CR, but then you could run this back on the data and get values per field that would differ, having chosen. They might not differ by much, but they could. So there's a very interesting question about, in my mind, about to what extent we should start thinking about metrics being ancillary variables. And then I've got some hard words, should, but then requested and required, because if people know something about the quality, of course, once I've got the compressed data, I don't have the original data anymore. I can't calculate any of these things. So I think if we're going to be talking about compressing data at large scale, we have to give people tools and encourage them in our methodologies to record information that potential users can understand how good their data was. Some other concerns, and if we start to blend into requirements, come from thinking about it from an operational concern. If lots of people are doing these things, whatever you need to do needs to be recognised internationally, and ideally it's an international standard. And ideally it's unencumbered by IPR issues, and in our world, perhaps a WMO standard's a good thing. You might think many of the common techniques that we use are already in that space, but some of them are maintained by national labs and have interesting IPR statuses. Maybe we can live with that now, but I think if one thing the last decade's taught us is that that the money that sustains our labs and the politics that sustains our international relations are somewhat more fragile than we think. And we're in this for the long game. Whatever you do needs to be reliable. Much data is forever, and you must be able to decode in the future. And so esoteric compression methods and software are a problem. We really want to trust in their maintenance, and that trust perhaps in a standardized view of them. They obviously need to be fast, and even in the RIF, they're starting to think about the difference between compressing and decompressing and where these things happen. And clearly they need to be scalable and granular, and decompressing fields versus decompressing chunks. What's a chunk? Did I compress over 4 dimensions? How big a chunk did I? These things all start to matter. As you'll not be surprised to know, the whole point of this talk at this meeting is all about arguing that this is another example of stuff that we don't put in files that we should. There's an information transfer between people and across time that we need to engender with our CF metadata. Yes, it's a cost to think about all this stuff in front at right time, but that cost is paid off. That's what you might call a metadata friction, but it avoids scientific friction later on when you don't know what's done and so on. So doing something about this for me is a given. So let's get a bit closer to home. Applications do scientifically informed information reduction. So the earlier things that I talked about, things like saying I'm going to do some averaging and remove some grid resolution, that feels to me like provenance. Now, we don't do much provenance in CF. We just say, oh, you can throw things into file or variable metadata in kind of unstructured sentences, and that's kind of fine. So to some extent, that's out of scope for CF, in the sense that it's somebody else's problem, but somebody should be doing it. But libraries do compression and decompression, and they can use lossy and lossless techniques. And thus far, I think mostly that's been a candidate to being opaque to CF. CF doesn't know about compression very much, although obviously the netCDF library knows about the filters that we used, and so in that sense, that's not opaque to CF, even if we don't think about it. At least we have access to it. But it certainly doesn't know what somebody did in the way of lossy compression before it got to netCDF. And so the question at hand is, what, if anything, should we be doing about compression information and encouraging it within our metadata conventions. And is it our problem? But if not, whose is it? Is the obvious question. To go a bit more detailed into what the actual requirement here is. Software needs to be able to inspect the filter requirement and request storage to call third-party libraries. That's essentially what the netCDF library does now. I think I've tried to motivate, we need to encourage and potentially promote the necessary metadata and software to do, to allow other parts of the infrastructure to do decompression particularly, like potentially even compression depending on where you are and what you're doing. You know, for example, compression could be done by the network card on an HPC CPU. But that's getting a bit esoteric, but certainly there is a requirement, I think, to be able to slice into remote chunks without bringing the entire chunk to the client. That's what I was trying to say this morning. And so that we can do the decompression on the remote chunk requires some changes in the way we think about the metadata and where it propagates down through our format libraries. So there's probably more implications for netCDF than CF in the first one. The second one is very much a CF issue, I think. We must allow users to understand what compression has been done, what the intended use case was, and provide some metric of what information content remains, whether that's an ancillary variable or whatever, or encourage the use of standard names that make those links and so on. And so the question I want to leave you with is, what does such metadata look like for both targets? And should we be talking about this? And Charlie will motivate some of this a bit more, and then we're going to talk about it some more. So I'll stop there. My last slide is the obligatory one, which is for the funders. So we'll leave it there.
Thank you, Bryan. I don't know if there is any question, comment, or we can pass to Charlie because there is also discussion. Yeah. Okay. Thank you, Bryan.
That are moving along, despite the fact that we don't have great answers to many of the questions that Bryan already raised. So we're doing the technical groundwork. And last year, you might know, if you were here, that we had another lossy compression session. And so I'm going to ask you to start thinking from a fresh point of view about what you think, in answer to Bryan's questions. What would the metadata look like to inform the users of lossily compressed data? What's happened to the data? Think of it from a fresh point of view. And then at the end of my talk, I will re-show the breakout summary from last year and tell you about some of the things that there seemed to be a consensus on and some of the things that maybe there was no consensus on at the end of last year's session. And I hope that will help us go into the breakout, those of us who choose to go into this breakout this afternoon, so we're not completely starting from scratch. All right, so I guess in conjunction with David, we decided that I would talk about the implementation of lossy compression in netCDF. I'm going to do that for about half the talk. And then I'm going to start switching over towards, so how would we, and how might we encode that in metadata that CF has a say over. So the first part will be more about the design of the netCDF implementation of lossy compression. And I want you to keep in mind, if this isn't your cup of tea, that all we're trying to get to today in this group is suggestions, opinions, questions about what kind of metadata we might want to make allowance for in the CF standard that will help users understand their data better. And so if you're not a compression person, you are probably a data user person. And just think of it from your own point of view. What would you like to know about the data that you'd received? Bryan gave the example of CMIP3 and CMIP5 users who had no idea that much of the UK Met Office data had already undergone quantization, lossy compression. Okay, so that's kind of the high level TLDR, I guess, of the talk. I will
try and motivate this by also mentioning that there are good kind of green computing related issues for compression. We are geoscientists. We kind of share responsibility for the data that we store in these large model and comparison projects, in model simulations, databases, and satellite archives. And it's storing too much data, much of which is random in terms of the bits we're actually storing, is unnecessarily emitting CO2 for absolutely no scientific benefit. So let's try and tone that down. I think that's as valid a reason to compress, probably more valid ethically and morally than many of the technical reasons you want to compress. Okay. So I'll start off with a timeline very quickly. This includes all compression in netCDF, lossy and lossless. So going back to the beginning of netCDF 4, it's always supported zlib, which you might know by its other name, gzip, so the GNU compressor. And that compressor, that codec, that compressor decompressor, has worked in parallel in the netCDF parallel PIO library, for example, for a few years. So you can do your compression in parallel on HPCs, and that's great. In netCDF 4.8, knew the option to run with non-zlib filters, with your own filters or own codecs, was introduced. However, these tend to have low interoperability, and the guarantee that you'll be able to decompress that data in the future is not there, really. And so we want to, in this session, focus on codecs that have high interoperability, are well documented, and are guaranteed to be around for a long time. 2 years ago, Ed Hartnett, now of NOAA, and I established a project to make codecs that were not well supported in netCDF land. It's called the Community Codec Repository. And we added APIs so that you could actually write data in netCDF from the get-go with any codec that you wanted to. And so this is not necessarily post-processing anymore. This is done at dataset write time. So you can link into these filter libraries. And then most recently, the exciting stuff that we're going to spend the rest of today's talk on is that this year in the netCDF 4.9 releases, that library, that C library, and Java and Python support these codecs, these lossy codecs. The names bitgroom, granular bitround, and bitround are going to come up again and again, so they're in blue. This series of this latest netCDF releases also introduced new fully supported lossless compressors that I won't say much about. There are their names: VZip2, ZStandard, BLOSK, which includes its own versions of ZStandard and zlib. And most recently, HDF5 decided it would start curating its own kind of database of well-supported lossless codecs mainly, but they could be lossy as well, like ZFP. And the goal here is really to make this support netCDF wide, and I think that's been done for C and Fortran and Python for sure. And then Ethan's talked about getting that implemented in Java. Okay, so what is this quantization that we keep hearing about? So in netCDF 4.9, anything can be lossily compressed via one of those three quantization algorithms. So these are algorithms that do rounding on the least significant bits of the mantissa or significand part of a floating point number, an IEEE representation. And because the rounding occurs at the end of the number, the least significant bits, the result is also an IEEE format. And so there's no decompression necessary for these quantization methods. Once the quantization occurs, you've lost your data, you can't get it back. You can prescribe, you must prescribe how much quantization you wish to do. And the two methods that the netCDF library supports, it depends on the algorithm. Two of the algorithms take a number of significant decimal digits, and one of the algorithms takes a number of significant bits. And so for single precision, you have about 7 digits you can deal with, and 23 bits, and then double precision is more. So those are the ranges that you can prescribe for your lossiness. And graphically, what's happening, there's an IEEE format number with a sign, an exponent. The number is pi. And then here's the number of significant digits. This is just meant to convey what happens. You can see, this is from bit grooming, and it's not the most efficient or optimal algorithm, but you can see the number of zeros increase. And so if you quantize in netCDF, you really need to use a lossless compressor afterwards, because what happens is the quantization just writes zeros, so you haven't compressed anything. But the lossless compressor is going to recognize these bit patterns, and it's what's going to do the actual compression. So these quantization methods do not themselves compress anything. They are pre-filters for a lossless compressor. Okay, and now graphically, I'm going to spend a bit of time on this slide because I think it's worth showing what the different portions of compressors do. Oops, I probably walked out of view, but
Okay, Charlie, we can see you everywhere where you're in front of the screen.
you can see me everywhere.
Wherever you walk in front of the
Yeah.
screen, you're visible on the video as well.
Yes.
Okay, so I can walk anywhere.
Yeah, almost anywhere. At the building, at least.
Stay in the room.
Yeah, there's a nice cerveceria down the street.
So,
Okay. So CMIP comes up a lot. It's just a kind of a great exemplar of large data set storage. And Bryan mentioned that lossless compression is required in CMIP 6. So if you think of a large file or data set, like a monthly mean output from the UK Met Office model or CESM, it's maybe a gigabyte in size, typically. That's kind of the size range they recommend. And then you compress it in CMIP 5. The compression ratio for a typical data set, atmospheric GCM output, was about 1.78. Okay, so this is the compression ratio on the vertical axis. This is the CMIP compression algorithm, deflate, or gzip, as it's otherwise known. And so all of the data in CMIP had occupy about a factor of 1.8 or 2 times less space than they would if they weren't compressed. And that's great. So you want your compression level, your compression ratio to increase. And how do you do that? You use lossy compression. It's interesting to note that some of this lossless compression is just due to the shuffle filter, which is another pre-compressor filter, and it's very good at getting those exponent bits that don't change very much to also be compressed and not take up storage space. So a significant fraction of the lossless compression is due to shuffling the data before you compress it. And so that's going to come back in the future, because netCDF was very good about essentially always shuffling data that you compress. But with all of the proliferation of compressors, you now need to kind of indicate that explicitly for some other compression algorithms. So this is shuffle. Some of the cyan and yellow curves is lossless compression. The vertical bars now are different lossy compressors on top of the lossless compression. And so to what extent does the lossy codec increase the value of the lossless compression above 1.78? So this is all due to lossy compression. And you see 3 bars. These are the 3 algorithms that netCDF now supports. 2 of them, you indicate the number of significant digits that you wish to retain, and 1 of them, you indicate the number of significant bits that you wish to retain. And you can see that generally, it's possible now to get, with deflate, compression levels up to on the order of between 5 and 6, if you choose the right lossy compressors. So that's a big step forward. This can all be done within a standard netCDF library. And we can at least do that good if we wish to sacrifice a few significant digits. So NSD equals 2, that might not seem like a lot of information's being retained, but as the Kluwer paper, Milan Kluwer's paper, that Bryan referenced suggested, in fact, that's enough for almost every field to store more than 99% of what we think the information content of that field is. So these are practical, these are attainable for most fields without losing scientifically significant information. This is not pie in the sky. Pie in the sky is a sort of a different, not as appealing. Numbers. I'm going to come back to the actual algorithms if there's any choice, if there's any questions later. I'll just point out that bitgroom was an algorithm that alternately shaves bits and sets bits, and it doesn't have very good error characteristics, but it was it gives good error metrics on average, but there's edges and artifacts that you don't really want, and that was an original sort of advance that's stuck in the netCDF library because it was the first one put there. Bit round is the one where we specify the number of significant bits, and conceptually it's probably the simplest. You just round the least as many bits as necessary to preserve the number of bits you want to keep. And you do that to every single floating point number in the field, without exception. So you're just trimming the number of bits at the end uniformly across the field. This is the algorithm that is in Milan Kluwer's paper. And so if you have an idea of the information content, or kind of similarly, the structural similarity index measure that Alison Baker developed, then you can feed that into the bit round algorithm, say I want to keep 15 bits or 2 bits or whatever, and bit round will do it. The next algorithm, granular bit round, has bit round in it, but granular bit round, rather than applying the bit round algorithm uniformly to all numbers in the field, actually preserves a number of significant decimal digits, and it therefore is able to trim a different amount of bits from every value. Okay, so you're going to compute how many bits you need to trim to preserve X number of digits for every value. So it's a bit more intensive on the front side, and it's called granular because now you're bit rounding each value with perhaps 7 bits for one value, 11 bits for another value. The range of these trimmings can be about 4 bits because there's about 3.2 bits per digit, per decimal digit. So somewhere in there. This is just to intercompare what happens if you use a different lossless compression algorithm with the same lossy algorithms as before on the same data set. This has changed. BZIP2 actually gives a compression ratio for this data set closer to 2 to begin with. And on top of that, you can see that these lossy numbers are now approaching a compression ratio of 7 for retaining 2 significant digits. So that's better, but BZIP2 is a very slow compressor. And so a compressor that many people use and that's become rather standard and is free and open and unencumbered to use and is used in the Linux kernel and will therefore be around quite a long time is ZStandard. And so netCDF supports both BZIP2 and ZStandard now as standard lossless codecs. And so with ZStandard, you can get compression ratios that peak on this plot at about 6.5. So one take-home message is that it's getting harder to find people or scientists who think that there's something discordant or wrong about trimming their data, because many studies of Alison Baker and Dorrit Hammerling and others have shown that you can preserve the scientifically meaningful information with only very subtle exceptions. And so it's kind of a unicorn with a rainbow situation where you're saving energy, storage, and the associated greenhouse gas emissions without sacrificing scientifically meaningful data. So all is hunky-dory. All right, I'm switching now to the sort of the second part of the talk. In the netCDF library, we now have these types of calls in version 4.9. So at write time, you can tell the library to use one of the quantization methods, and this is how you pick between the 3 currently supported lossy algorithms. It's called the mode. So bit groom or granular bit groom or bit round. And for the lossless algorithms, it used to be there was only a deflate function. Now there's a ZStandard function, a BZIP2 function, and there's always been this kind of generic function for a long time for any filter that you might want to use, as long as you have it in this HDF5 format. So these are all there. And that means we no longer have to do compression in post-processing. If you have a lot of data that you want to compress, it came from a model uncompressed, for example, and you've decided I want to shrink it. You used to have to do that in post-processing, but now you can do that at write time because you can have your model call these functions, and when the data is written, it will be compressed. So that's what I mean by end-to-end model-to-archive compression. You don't have to reopen your data if you don't want to. So those are features that the library exposes. It's not very user-friendly to apply these algorithms with the available netCDF, with the tools that come with the netCDF library, such as NCGen and NCCopy. Maybe it will be so. For now, NCO, software that I've written, does access these in a pretty simple way, I guess, maybe user-friendly. So here's an example of how you might do it in post-processing with modern codecs without memorizing HDF5 filter parameters, which are not user-friendly. So if you now give a compression string option to NCKS or any NCO operator, and you tell it, and here's the syntax, so it's just codec, pipe, codec, pipe, codec. And the abbreviations are granular, bit round, shuffle, Z standard. Okay, so you're telling NCO, do the lossy compression, granular bit round, use a shuffle algorithm before you losslessly compress it with Z standard. And there's default compression levels built in, and so because you don't specify the compression level or the number of significant digits, it's going to use the default, which I think is 3 significant digits. So that's what the output will look like. You can use NC dump minus S or NCKS minus hidden. And for a field like surface pressure, I've highlighted in blue what the attributes of the compressed field look like. So you'll see that the lossy compression algorithm in the netCDF library appends one new attribute. And it's a library algorithm because it's led with an underscore. So underscore quantized granular bit round number of significant digits equals 3. So that's what that command did. And it's actually the first attribute written. You can tell because it appears first. So then there's some standard things that got copied from the input data set. And the next blue attribute is compression related. And it's just telling you that, remember, compression only works on chunked data. So you've got to make sure that you write in a netCDF4 format in order to get compression to work. If you have a netCDF3 data set, you try and compress it, you will receive an error that it can't be compressed because it's not chunked. So it's chunked. Oh, there's the chunk sizes. It tells you the filter that it used for the lossless compressor. Remember, the lossy compressor's name is right here. The lossless compressor is written in this HDF5 code. You can get the name of that printed out if you put a debugging level in there. It will print out Z standard on the side there. That's telling you that it was shuffled. So those are the types of attributes that are currently in the netCDF library that are automatically written. And what we're here to discuss in this session, and then possibly to start drafting some implementation ideas in the hackathon, is what are we missing? What would you like to see? Because this is lossily compressed data. And that's right now all that's written. Just to mention, this all works with Zarr. Transparently, it looks kind of the same, except for the specification of the input and output files has changed. So that's the beauty of the netCDF API. The library backend took care of all the other stuff to write it in Zarr. As a summary, the netCDF library currently will write one of these 3 attributes depending on what lossy compressor you invoked. And the library maintainers are reluctant, should I say loath, to add any more attributes to the library side. So it's up to the CF community, effectively, if there are more attributes desired, to put them on the user space side in data sets because of what I just said. I want to keep the library clean, and these are very long strings to keep adding into the library code. So what might we want to add? So what's currently in there, we're recording the number of significant digits or the number of significant bits. What else? Bryan mentioned many good ideas that I don't have on the slide, so keep those in mind. So he had the structural similarity index. You could think about potentially adding an information content method from information theory, such as Milan-Clower's article includes. You could think of other metrics. The most common field-wide methods that I could think of are kind of maximum error guarantees. The relative error, meaning relative to the number that was unquantized, what's the maximum error that any single element in this field is going to have relative to its original value. You could also have an absolute error, so just not relative to the original number, but on its own, what's the absolute error in the field? So a dimensional number rather than a non-dimensional fraction. And what would those be for the current algorithms? So for the number of significant digits, if you have a raw data value S, and it's the ith element of your array, what you do to determine the number of significant digits is essentially take the log base 10, because these are decimal digits, log base 10 of the original number, add 1 to it, and you're guaranteed that the difference, the absolute error, in other words, between the raw and the quantized value with a twiddle, that's the quantized value, the difference will be less than half the value of essentially the ones place in the ones place in the exponent field of your least significant digit. So, for example, I don't know. I like the 800-pound gorilla example. So is it really an 800-pound gorilla or is it an 805-pound gorilla? And if you want to maintain, 2 significant digits and your original number is 805, then 800's great, right? You're actually maintaining 3 significant digits there, because the third decimal out, so 800, so the ones place, half of that is guaranteed to 3 significant digits. So that would mean 1/2 a pound. So if you had a number 805 your quantized value will be no worse than 805.5 or 804.5 to 3 significant digits. And that's a pretty accurate representation of 805. Okay, so 1/2 of the value NSD digits in will be maintained. Number of significant bits. So this is perhaps easier to conceptualize. You're just trimming bits. So and each bit is a power of 2 in the IEEE format, because you factored out the exponent field. You're just talking about precision now. And you start off with this leading factor of 1/2, because IEEE has an implicit bit that you can't get around. You can't actually trim it because it's there implicitly in the formula. So in the end, if you want to keep, say, 10 significant bits, those are 10 explicitly stored bits. It doesn't count the implicit bit because you can't get rid of it. And the precision then is 2 to the -10th times 1/2 for the implicit bit times the original number. So relative measure. And kind of winding up now, last 2 slides. The last year's summary, we had a breakout and we asked people, this is what the netCDF library is going to do. What would be a more CF way? So sort of more extensible, more open to different implementations, preserving the provenance of where the codec came from, of encoding that information. And people came up with 4 separate kind of pieces of information. And instead of being chained together like a giant string, that they might like to see in a lossily compressed data set. And these are the 4. The name of the family, which in this case would be quantization. So something indicating quantization. The actual algorithm, that's a quantization algorithm. So you might have There are other algorithms you could think of. Whose implementation? Because you can have more and less optimal, you can have buggy implementations as well. So you want to know if your architect of the implementation was the netCDF library or some guy named IMK. And the level of lossy compression expressed in the most natural way possible, digits, bits, whatnot. So those were the 4 thoughts. We didn't actually mention too much any floating point metrics. And the kind of the questions that we asked for feedback on were, does quantization merit storing additional metadata? And most people thought, yes, this is something that we should think about. What were the attributes that you might want to add? So I already showed those on the previous slide. And then I added this one. I think we might have discussed it. So a 5th would be some kind of maximum, some kind of error metric and floating point. This could include the structural similarity index, the information content, user imagination. There was some discussion about whether this should be in the netCDF user's guide or in CF. Could this be implemented at the netCDF level? Since CF adopts the netCDF conventions as part of CF, should it be done there? And Ethan was thinking at the time, yeah, maybe we're going to try and open up the user's guide to a more community-oriented format. And that was never really resolved. We decided, I don't know, the group decided this, but it just seemed like the lowest hanging fruit was quantization methods. We weren't going to think about all possible lossy compression methods because there's so many ways of doing lossy compression that coming up with first some metadata for a simple method like quantization would then lead to possibly future modifications to account for things like, I think ZFP or ZFP does a very advanced type of lossy compression. There are other algorithms, LZP, for example, that were talked about at that compression meeting that Bryan mentioned in February, the online one. So these are doing lossy compression or able to do lossy compression. I'm not sure how you'd store that information, though. So I think at this meeting, we're going to try and focus, if we can, on the low-hanging fruit quantization, with the idea of it being extensible. And we asked if there were people interested in further development. And at the time, 2 people raised their hands, David and I, and now possibly you. If you'd like to contribute your ideas, that would be great. We'll see you in the breakout. And now I think we want to stop and ask for any questions, comments, or feedback on either of the last 2 presentations, Bryan or my own. Thank you. See 2 hands, Steve.
Yeah, this is not so much on the metadata and what the discussion is going into, but as a infrequent netCDF user, although and only a user, I don't tend to generate them. I've not seen much in the way of this compression stuff at all, but what I have seen is that the old kind of scale factor and scale offset stuff, which I gather is used to like allow you to use integers instead of floats to save data. Where does that fit into all this compression stuff, and how does that apply?
Okay, yeah.
Or is that just old hat now?
Yeah, that's a tough word, but sure. So we've evaluated that that's a form of lossy compression that we call packing. Specifically in netCDF, it supports linear packing. You can also imagine exponential packing or exponential scaling, and HDF supports that. And I think that the buffer standard might be able to use that as well. Yeah.
I think so. Yeah.
I think so.
Grib as well.
Yeah, Grib as well. So those are called, so linear packing is what you're referring to in netCDF. That's still supported, it's still part of CF, but it has very poor error characteristics. The range of packed values is only about 5 decades of values for a single precision float. So for things like surface pressure or mixing ratios for trace gases or dissolved gases in the ocean, it's just horrible. Okay. So we're not going to try and mess with it, but it's still certainly valid.
Sure.
Great
Okay,
question. Yeah. Okay, George.
So looking at those 5 attributes, it seems to be an assumption that you're only running a single type of lossy compression, but if you have these same data files for a long period of time, you could say, I don't know, quantize at a certain value once, then 10 years later, do a different compression that introduces some noise, and then quantize again at a later point, which would be affected by that noise. And to rebuild it, you'd have to know the order of the algorithms that you wrote, and I cannot see a way to represent that yet.
I'm not sure I understood if you were saying that you quantize it not very much, and then you decide later to quantize it some more, and then some more, because you can't go backwards. Once it's lost, it's lost.
But you could do a compression that introduces non-zero bits to the quantized area. You probably shouldn't, but if you have data for 30 years and say you work for somewhere that's automatically applying these, and not that you can reduce, like return it, but you would not want to know what was happening to make sure that your data was actually representing the processes that had happened to it.
Well, and a concrete example of that point might be if I have 2 quantized data sets and I do some calculation, I then have a effectively quantized data set, which is there's some and then I'm going to quantize that.
Yeah, and so that people do that all the time, combine data sets, right? You want to have your observation minus your model divided by your observation or something like that. And if they're all quantized, then the result of that process that this is an example of, would be non-quantized values that started out quantized, and then what do you do? And that is difficult. That's a great question. How would you do that?
Yeah, I think that the simple question is, if I'm running multiple compression algorithms, how do I represent multiple compression algorithms with those 5 attributes? Or in your
I think that's a great question.
Maybe just one comment about that, because when you were explaining how the compression are being encoded, I was thinking on the cell methods of programs, for example, because it's a kind of processing the data. But this could be a kind of compression methods. That is just one attribute with chains of
a chain.
As we do for the cell methods. I mean, it's not a cell method itself, but just the same semantics or similar. Just you are able to add compression method instead of having a plethora of this only 5 attributes. But and also because I see a conflict with the netCDF, I like to say property, no attribute, because in fact it's a property of the netCDF, the compression attribute that you mentioned, right? Not attribute itself. It's a property of the variable of the netCDF. I see a kind of conflict over there also, yes, with the call everything attribute, and also having many attributes for encoding the lossy compression. And I was thinking this process of compression just a change of pipes of methods to be applied. Just an idea, okay? It's not.
I think that the parameter space that opens up is so vast that it makes me want to scream quietly into a towel. So really one of the things to be careful about, and that is to recall that what netCDF is doing when it's writing this is effectively it's writing it like a fill value. The quantize algorithm, the quantize attribute that it's writing has an underscore in front of it, which means users are not supposed to muck with that. And so if you decide to take a number and you decide to do a field that's already been quantized and you want to do something else to it, to that specific field, it's actually you're kind of violating the API guideline if you manually change that attribute anyway.
Well, hang on, Charlie. I've got. Sorry, I think I've got a horrible use case in mind, which might be rubbish. But so if I legally take something that was quantized and then compressed and on a chunking with a chunking algorithm that was a particular chunking algorithm, and then some of these compression algorithms that aren't quantization are kind of doing look ahead across the algorithm across the numbers in that chunk, right? So so I read this in and then I chunk it out in a different way. Now I haven't done anything naughty, but I've changed the chunking, and my original description might have been relevant to the chunking that was originally there, but not to the new chunking.
Yeah, I see what you're saying. So that would make the original chunking attribute kind of invalid.
I'm
It
not
wouldn't
sure.
apply to the new chunking. And what that is a great example of why I think we decided, or why one natural boundary for the discussion here is just to think about quantization methods and lossy methods that don't depend on the chunking.
Yeah, no, it's good. I mean, I think limiting the scope is a fantastic way of getting started, because otherwise we're stuffed.
There'd be dragons there.
Yeah, but I think it's quite good to have some knowledge of the dragons, because it kind of tells you where not to sail right now.
Correct.
A lot of the questions that we're fielding right now also seem to imply, they seem to overlap with questions of provenance and not compression as such, which I would say is a whole different kettle of worms at the moment.
All right, so even with that restriction that I can only quantize, let's say I've got the number 0101, and then I quantize it, removing or keeping the second, and then remove it keeping the first significant digit. And I do that in the reverse order. Because that 0 is in that center, the interpretation of what a significant figure is on the second one will be different for both results. So the order matters.
Yeah, you can't. I mean, so each bit multiplies a power of 2. The order matters because your algorithm is supposed to work on the least significant bits. So if you remove the most significant bits first and then the least significant bits, that's different than removing the least significant bits and then the most significant bits, right?
You need to think about this, but maybe this is a lunch talk.
Sounds like a hackathon.
I think one thing to keep in mind is that the methods that have been implemented are quantization only in netCDF, and that CF depends almost entirely, less and less so, but still almost entirely on netCDF. And so this is thinking about these quantization methods is a more practical import. And underlying the methods is that they're not reversible, and they don't mix well with each other, because you won't get well-defined properties if you mix, even amongst variables that were encoded with different lossy quantization algorithms. So I showed you the error statistics. They're very dissimilar amongst the algorithms, and that is just one of the way it is with lossy compression. You can't go back.
Yeah, I agree. So can I slightly change the subject towards Daniel's point about we're talking about provenance? I mean, because we are to some extent, but a lot of CF is about enabling what we think is important in provenance to be described. It's a subset of provenance, right? And even in the response to this set of questions, Charlie has to have kept coming back to saying, well, I'm just talking about quantization. Well, I'm not talking about ZFP. I'm not talking about SZIP. But those are all equally valid ways of addressing the problem. And some of them are more amenable to having a scalar essentially a scalar variable attribute, whether it's a string or whatever, but one number, one set or set of small per variable. Some of them are probably more amenable to having an ancillary variable. And it seems to me that the dragons exist somewhere in this space, but we're also trying to find a set of a limited set of provenance that describes a limited set of use cases around compression. So I just wanted to head off that we shouldn't talk about this because it's provenance by saying all of CS provenance really. It's just we choose which bits we want to talk about, and I think we need here, if we're going to do something like you proposed on the slide that's still up, which I think is great, then we want to put it in a space where we say, and there's a limited space of other things we might want to fill later. Yeah, I'll stop.
If I can make a comment on this, Bryan, is what we are doing, or what Charlie has explained, is there is something that is application level. You are quantizing at application level, and there is another thing that is you are quantizing at storage layer. And the question is, how much information, how many information do we want to move from the storage layer, quantization on the netCDF library or CDF library, or there's how many information we want to move to the application layer. And when you are talking about the attributes for encoding the quantization, this is application use. Is because the person that is writing the data wants to write down the provenance, what's happening to the data. And he wants to move also to the storage layers in some way, in a specific way. I mean, what I see here is we are mixing it, because probably there is somebody just writing the data, and this person doesn't want to encode what's happening. Or yeah, I think that's one of the questions, or one of the things, because we are talking about two layers, different layers, and I am thinking of you to beyond of the beyond of the netCDF.
Are we talking about two layers? We're definitely talking about things that need to be separated, but I'm not sure the number is two. I guess that's what I was talking about before, because when I was talking about where is the decompression happening, to some extent the application will know where it wants to do decompression, because at the end of the day you've got to decide, I know I'm loading the data from a data center on the other side of the world, or I'm loading it from the hard drive. I'm going to use decompression in my software, or I want to do decompression on the remote server. So there's an element of everything that's in the storage layer has to be available to the application.
So the application can determine, if I'm following you correctly, whether or not, for example, the data's already been decompressed by an intermediate network card or intermediate server. So there's actually, that's a piece of metadata that's not explicit, that wasn't explicitly listed on this slide here. Yeah. So that's something CF might consider as well. I wanted to point out there's some, if you download the talk, there's some links to the papers that have been mentioned. And then I wanted to, sort of speaker's prerogative, remind you that this is what the users are going to see now. That's it. No, the dataset writer that put in no extra effort to make this, pre-CF compliant. This is what's there. And as a user, do you find that sufficient? There is, of course, also the history attribute. And so if this was done in post-processing with a tool like NCO or CDO or something like that, then there will be stored in the history global attribute some command that actually is a little bit more informative about what history this data set's gone through. But if this was merged with another data set, then that history attribute becomes kind of incomplete.
You're lucky if it's there at all. Can I just add another thing, Charlie? I think not only is this what they see, and I think the subtext to what you're saying is, well, it's a little bit opaque, isn't it? Not that it won't even see this unless they actually go looking quite hard. I don't know whether that's a default output from NCO NCKS, but it's not the default output from NC dump, right? NC dump hides all those underscores by default.
Yeah, so
you're not going to see this stuff unless you really want to, and that's a little bit, I think, problematic.
But these are not. I mean, it's what I was saying before. These are properties of the stories. They are not attributes of the variable.
Well, I know. I would suggest that the fact that it's been the lossiness of it is a property of the variable. The lossless storage mechanism is a property of the format. Yes, but the fact that you did lossy operations on it is absolutely a scientific property of the variable.
Precisely. Yes, you've changed the data.
But if the user changed the data in the application level.
Yeah. So the
you
data
can annotate as application level as a down attribute that you has quantified the data, and then just go to the format. So to the storage layer, just to make whatever.
No, but the quantization decisions that are changing the information content of the data, not how to interpret the bits stored, those are of a scientific nature, and they should be exposed to scientific users.
Yes. I agree with that. We are discussing what to expose to the user itself. What we want to expose, but sometimes also how much information has to implement the user also for the storage layer. I mean, all the attributes that we are talking about quantization can be different as the encoding in the storage layer.
Yeah, I think what you're saying, Antonio, is yes, there's a storage layer set of variables and we're looking at them. How you present that to the user in the application level is kind of what the CF problem, and that might be a different vocabulary. And that's pretty much exactly what Charlie's saying. Let's do something better than 32015, 3.
So
yes.
Let me add kind of a bit of trivia that's actually more important in the sense that this is just the netCDF C library implementation of 3 algorithms. And the C library made the decision, because it's a library implementation, that they would prefix this with an underscore. You can, and I have, implement these algorithms at the application level in your own applications and do the exact same processing. And what NCO does when you invoke these algorithms, not through the C library, but through NCO, is it outputs the same attribute as this one, but with no underscore. So the user would definitely see it when they did an NC dump. It was just a viewpoint of, that was a handwritten application that I wrote. I wanted to see the attribute. The netCDF library writers have a kind of a different set of concerns, and so they prefixed it with an underscore. But we want to make sure that the user, I think my goal is to make sure the user understands the data processing that the variables have undergone. And if you go, if you have a very long time to read documentation, you can see in the NCO manual the description of what I think best practices are for lossy and lossless compression per variable. How do you do it? How do you do it in one command for an entire data set where certain variables have 5 significant digits and others have 4 and others have 3? So you got your mixing ratios, then you've got your fluxes, and then you've got your clouds and aerosols about which you really know nothing. So you've got different compression levels. How you do that all at one time, and that's described in the manual. And the user should be able to see the different per variable information from the get-go, I think. And so that's how I've approached the issue. I'm kind of speaking with 2 hats here, and that was my NCO hat, which is really oriented towards getting the users what the users want to know and want to do. I think that's CF's role as well. Not to coddle those library writers, but do what the users would want you to do.
Okay. And then there's more comments.
I just want to say that was a really good talk. I'm not a lossy person. I learned a lot today. It was really well portrayed, easy to understand and follow.
I appreciate it.
Thank you very much.
Thank you.
Just, I think you just said it. I'm trying to type stuff, so it's things a bit asynchronous in my head. Yeah, so having this stuff is about it always being available. The fact that those 3, the various background friendly backgrounds are in the netCDF library, that means that's how they're going to get used, say, in Unit 7. So the fact that you could apply these later, I think that's important, is and how you record that or separately is sort of maybe that's a secondary question. If we focus on what's currently available to everyone, guaranteed. There's so many ways you could say extensively. What if we have new codecs that user wants? I'm just saying maybe we don't want to worry about that now. That may have been already said by you earlier. But again, it's limiting the scope to being.
I am so I think there's I'm totally in favour of limiting the scope, but the reason why Alison Baker's done all this work on compression is they're looking at the next large ensemble, right? And I think we're going to see single model large ensembles dominating data in our community in the near future, not CMIP 7, and they're almost certainly going to make choices around using one of the other methods which give you even more compression, so I think this is one of those situations where events are going to overtake us quite quickly. So while I think I'm totally in favor of solving the problem that Charlie has put in front of us first, because it is tractable and bounded, I think we've got to realize that right next is coming these other lossy compression methods,
which won't be supported by netCDF possibly.
No, well, they are supported by netCDF because they're just done before. That's Charlie's point. They're just not done by the library itself. The library itself's just compressing some numbers, and it's got to, so that in that sense they're supported by netCDF.
But not natively like these 3 are.
Not native, no.
Okay. That's correct. 2 of these libraries, one I think is named LZP, and one is named ZFP. They're very powerful. One of them did not have a 1.0.0 release until the last 2 months. And so its guarantee of stability in the API wasn't even there until a month or 2 ago. And so that was one good reason we didn't incorporate it like Z standard that's been stable forever in relative time scales. But I think that now that one has declared we're sticking with this API and this is going to be good forever, makes its appeal to incorporating as a standard in the netCDF base library, much greater, exponentially greater. So as Bryan is saying, there are other powerful libraries. Not all of them are going to stop changing themselves in the near future so that they can always be decoded, the version that they're writing now. But one of them has, and that's where we need to make sure as a community that we're using those libraries that are guaranteeing back compatibility into the future for storing lossily compressed data.
Absolutely. That's why I brought out that point, hopefully from the ECMWF experience. That's what they want. That's kind of mandatory before they'd use it. And I think probably before any of us with large archives would either.
Okay.
Okay.
Yes. Yes, we are finishing. Thank you very much, Charlie. Thank you very much, Bryan.
Thank you very much, organisers, because that actually worked as a hybrid with me and Charlie much better than I thought it would. Thank you.
Thanks, Bryan. Thanks.